Alright, welcome to lesson 3.02. Here we're going to be rewriting rational expressions in different but equivalent forms. Think simplification. Alright, so to get us started, go ahead and work through, copy down and answer problems 1, 2, and 3. Okay, so let's think about how we can simplify each of these fractions. So notice that you can rewrite these fractions in a way that allows you to simplify. So 5 is 5 times 1, and 15 is 5 times 3. Now, 5 divided by 5 is the same as 1 divided by 1, and so my fraction simplifies to 1/3. Same thing here. I can rewrite this. The common factor that 27 and 36 have is 9. So this is 9 times 3, and this is 9 times 4. And so since 9 divided by 9 is 1, all I'm left with is 3/4. All right, C is a little bit trickier. I'm looking for a common factor that I can cancel. Now, notice that the square root of 75, I don't know what the square root of 75 is, but within the square root, I do know that 75 factors nicely. And since I'm square rooting, I don't want to think about factoring it with 5, thinking about what times 5 equals 75. But because I'm going to be taking the square root, I want to think about 25. So what could I multiply 25 by to get 75? Well, that's going to be 25 times 3. So I have the square root of 25 times 3 divided by 5. Now, I know that I can take the square root of 25 times the square root of 3. I can rewrite this. Square root of 25 times the square root of 3, and divide that by 5. And since the square root of 25 is 5, I know that I have two common factors, 5 and 5, and I can cancel those. Those are just 1/1, and so I'm left with the square root of 3/1, which is just the square root of 3. Here I have pi to the 4th divided by pi squared. So thinking about this, I can rewrite this as pi times pi times pi times pi divided by pi times pi. Well, pi divided by pi is 1. Another pi divided by pi is also 1. So now in my numerator I have pi times pi, which is pi squared. And in my denominator I just have 1. So I'm left with pi squared. What you'll notice is that the rule we've come up with is that if I can factor out a common factor, and I'm looking for the largest common factor that the numerator and denominator have in common, then when I cancel those out, because something over itself is 1, I'll be left with the most simplified version of the fraction. And we'll illustrate this in a second. Now, whether or not this rule works for rational expressions is a whole nother question. What if I don't just have constant numbers, but I have variables involved? And what we'll find is that this seems like it should work because I can factor out things with variables, right? I can write them in terms of factored form. So we should be able to do the exact same thing. There is just one thing that we'll have to keep in mind, and we'll discuss that in a second. All right, so the general rule is this. If the numerator and denominator have a common factor, we can divide out the common factor and simplify the expression. So it looks like this. If you have n times a divided by n times b, then I can rewrite this because n divided by n is going to be 1. And so I'm left with a divided by b. So anytime I can factor something out, I can cancel it because it will be divided by itself. And the same holds true for all rational expressions, but we must be sure not to forget any values that make the expression undefined. So let's take a look at an example to make this clear. Let's consider this rational expression here. Now, before we go and simplify it, we have to remember the difference between rational expressions with variables in them and the fractions that we just worked with. And the difference is that those fractions, we already checked, it's really obvious from looking at them, that they don't have a denominator of 0. Because if so, it wouldn't make any sense. But for these rational expressions, before we do anything, we have to consider that there are going to be some x values that make this expression undefined. So before we do any simplifying, let's find all the x values that make this rational expression undefined, so that when we simplify, we can be careful to say, make sure that you do not evaluate this expression at any of those undefined values. So go ahead and do that on your own, and then we'll take a look together. Okay, so as you'll recall, a rational expression is undefined when the denominator is equal to 0. So we set our denominator equal to 0 and solve. Here we can factor this nicely, and so we can see that the denominator will be equal to 0 when x is equal to -3, or when x is equal to -1. Now, that we have that in mind, we can go back to our rational expression and try and simplify it. Try and write it in a way that makes it a little easier to get a grasp of. Just in the same way that when you looked at those fractions in the discovery problem, when you wrote them in a more simplified form, it was a lot easier to grasp. When we have 5/15 and we rewrite it as 1/3, it makes a little bit more sense. And so if we can do the same thing with this rational expression, hopefully we can make more sense of the situation. Now, just as we've done with fractions, whenever we have a rational expression and we want to simplify it, you want to write this down, we need to factor the numerator and denominator and then cancel out any common factors. So let's go ahead and do that here. The numerator, you'll notice, can't be factored, but the denominator can. We already did that in this step here where we determined any undefined x values, any x values that make the expression undefined. So we've kind of already done all of that work, and we can rewrite this as x plus 3 times x plus 1, just as we did with those fractions where we factored the numerator and denominator. Now, notice that the numerator and denominator have a common factor. In the numerator, I have an x plus 3, and in the denominator, I have an x plus 3. And notice that x plus 3 divided by x plus 3 is almost always going to be equal to 1. The only time it won't be equal to 1 is when it's 0 over 0. And we've already accounted for that. We know it's going to be undefined when x equals -3. So everywhere else, we can cancel this, and we can say it's going to have the value of 1. So x plus 3 divided by x plus 3 is the same as 1 divided by 1. And I might put parentheses around this x plus 3 just to make it really clear that I am canceling this factor with this factor. Now, when I rewrite my expression, I simply have 1 over x plus 1. Notice how much easier this is to deal with. And the only thing that I have to make sure I remember is that this expression, just like my original expression, is undefined when x equals -3 and when x equals -1. So I can say that this expression simplifies to 1 over x plus 1 so long as x is not equal to -3 and when x is not equal to -1. And that's still clearly obvious when I'm looking at this expression. So here I've simplified and I've noted that there are two special x values for which this expression is not going to be undefined. So if I'm graphing this expression here, I can graph it everywhere except when x is equal to -3 and when x is equal to -1. But notice how much more simple this expression is than this expression. So simplifying rational expressions is going to be very helpful and useful, but we can't forget that there are some undefined, some values that make the expression undefined that we cannot lose when we're simplifying, because we want to keep the inherent value of the expression that we were dealing with. Let's go ahead and practice on a couple of problems. All right, so for both of these rational functions here, I want you to find the domain and simplify if you can. So what I want you to do is first find the domain. You've already done that, and so you want to go ahead and find the domain of each of these functions on your own. Then we'll check the domain and we'll simplify if possible. So looking for the domain, we know that the domain are all the x values except any that make the denominator equal to 0. So we have all real numbers except when our denominator equals 0. And when we set our denominator equal to 0, we can solve by factoring, and we get x equals 0 and x equals -2. Now, this factoring is actually going to help us out, because when we go to simplify our expression, f of x, we'll want to factor both the numerator and the denominator. So the numerator will factor to x plus 2 times x plus 2, and our denominator we've already factored as x times x plus 2. Now, notice that x plus 2 over x plus 2 is going to be 1 everywhere except when x is equal to -2. Obviously, then it will be undefined. So we can say this is the same as 1 divided by 1, and that allows us to rewrite our expression in a much more simplified fashion. Now I'm left with x plus 2 divided by x. I just have to make sure I say that this is when x is not equal to -2. Remember, if it were equal to -2, our original function would be undefined. And so we say when x is unequal to -2, and we should just go ahead and include that we can't have x be equal to 0 anyways. It would be undefined, and that's pretty obvious still in the simplified form. So here we've simplified our expression, our function f of x into a much easier to handle function. All right, go ahead and do the same with b, and then move on to number 2 and complete that on your own. For part B, I'm going to put the answers here in a second, and so you can check your answers. And for number 2, you should be able to come up with a couple on your own without my help at all. But make sure you've done those, think about them, and be ready to present your solutions in class tomorrow. All right, I'm about to post the answers for the answer for part B, so if you haven't done so already, pause the video.